Welcome back to AI.Code.Cast. We love to, dig into those coding challenges that really make you think. And this time we've got a classic. It's called the Skyline Problem.
Yeah, and what I find really fascinating about this one is the visual aspect of it, right? Like, imagine you're looking at a city skyline. It's really just a bunch of buildings. But what we see, what we perceive is that, like, outline, that silhouette where the heights change. And that's what we're actually trying to compute. Efficiently, of course.
Exactly. And you know what's really cool? Our listeners sent in some really creative solutions to this one.
No, yeah.
Yeah, some of them are brute force, some are incredibly elegant.
Yeah.
It's like we're architects today, but instead of blueprints, we're using algorithms, right?
I like that. So just to be clear, right, what we're talking about is our input is a set of buildings. Each one's defined by its left and right x-coordinates, and then obviously its height.
Right.
And what we want to output are those key points that make up that skyline silhouette, those turning points.
Okay, so let's unpack the challenge a little bit here. It's tempting to just, trace the top edge of every single building.
Right.
But that would be way too many points for our output.
Yeah,
right?
yeah. We don't need all that.
We only want those points where the height actually changes.
Absolutely, and that's really where the efficiency challenge comes in. A really naive approach could easily get bogged down with just tons of unnecessary calculations.
Yeah. So if I were to try just a brute force approach, where would I even begin?
Well, you could start by figuring out all the unique x-coordinates where building edges occur. So that would give you a set of all the possible points, right, for your skyline.
Okay, so got all those points. Then for each of those x-coordinates, I'd have to figure out what the tallest building at that point is. Does that mean I'm checking every single building?
Pretty much, yeah. You'd be scanning through your list of buildings, see which ones overlap that x-coordinate, and then you just keep track of what the maximum height is.
Okay, I can kind of visualize that.
Oh.
It's like taking a snapshot of the city at each of those x-coordinates.
Right.
And noting down the tallest point. But especially with a large number of buildings, that sounds computationally expensive.
Very much so, yeah. It's very intuitive, but it has O of n squared time complexity.
Right.
Where n is the number of buildings. That's not going to work if we're dealing with, massive cityscapes.
Yeah, not very efficient. So how can we avoid checking every building at every single point?
Right.
There's got to be a smarter way, right?
Yeah.
What if we tried to process the buildings in a more organized fashion?
Okay, I like where you're going with this. What if you imagine a vertical line, we call it a sweep line, and it's just moving across the city from left to right. And as that line encounters building edges, then we can update our understanding of the skyline.
Oh, okay. I like that. I'm seeing it. Okay, so the sweep line moves, and then when it hits the left edge of a building, we take note of its height.
Right.
What about when it reaches the right edge?
That's when we know that building is no longer part of the skyline. So we need to find a way to kind of remove its height from our calculation.
Okay, so we need a way to keep track of which buildings are active at any given point, the ones that are currently intersecting with the sweep line. Could we just use a simple list for that?
Okay.
We add buildings as the sweep line encounters their left edge and remove them when it hits the right.
You're on the right track. But remember that the skyline height at any given point is defined by the tallest building that's currently active. And a simple list would still force us to iterate through all those active buildings to find the maximum height.
Oh, you're right. So we're still stuck with that O of n squared complexity. We haven't really solved our efficiency problem. What if there was a way to just instantly know the tallest building without having to search through a whole list? Like, we need some kind of data structure that inherently keeps things sorted by height.
Now you're thinking like an algorithm pro. So what kind of data structure comes to mind when you need things sorted and you need to access them quickly?
Ooh, a priority queue. That's it.
Exactly.
That keeps the elements sorted, so the maximum is always right there at the top, ready to go. Okay, I'm starting to see how we could use this for our skyline problem.
Yeah?
Yeah, this could really change things up.
All right, so let's break down how this priority queue sweep line method would work. First, we still need to get all those building edges, left and right, along with their heights. Then we sort them all by the x-coordinate.
So we're lining up those edges in the order that the sweep line's going to encounter them.
Right.
Okay, and as that sweep line hits a left edge, we add the building's height to our priority queue.
Exactly. And the priority queue is going to automatically place it correctly based on the height, making sure that the tallest building is always at the top. But here's the tricky part, all right?
Okay.
When the sweep line hits a right edge, we can't just remove that building from the queue right away.
Wait, why not? If it's not part of the skyline anymore, shouldn't it just go What am I missing here?
Think about it. What if you have a shorter building that ends before a taller building that's behind it?
Okay.
If you just remove that shorter building immediately, the taller one's going to become visible too early, and that'll mess up our skyline.
Okay, I see the problem now. We have to be really careful about when we remove buildings from the priority queue.
Yes,
They should only be removed when they are absolutely, positively no longer contributing to the skyline. It's like they need to retire gracefully.
I love that. That's a great way to put it. The key here is that we need to delay removing a building until it becomes the tallest one in the priority queue.
Right. Because only when it's at the top can we be totally sure that it's not influencing the skyline anymore. It's like a building's grand finale,
Mm.
reaches the top and then gracefully bows out.
Exactly. And that ensures that we capture all the correct height transitions as that sweep line keeps moving. And with the priority queue doing all the heavy lifting, managing the heights for us, this approach is way more efficient.
Okay, I'm really liking this solution. So at each x coordinate, we check the top of the priority queue, and that's our skyline height, right?
Mhm.
But we only add it to our output if the height has actually changed from the previous point, right? We don't need all those extra points.
Absolutely. No need to add any redundant points for all those horizontal sections. And the best part, this priority queue method brings our time complexity down to O of n log n,
Wow.
thanks to the sorting and those efficient priority queue operations.
That is a huge improvement over brute force. But before we move on, I think it's important to touch on some potential pitfalls.
Yeah.
What are some common mistakes that people make when they're working with this priority queue approach?
One really common one is handling buildings that share the same x-coordinate. So imagine two buildings that both start at the exact same point. You need to make sure that you add both of them to the priority queue before you check for a skyline change at that x-coordinate, because the order that you process those edges matters.
That makes sense. We don't want to miss a sudden jump in height just because we process things in the wrong order. And of course, we have to be super careful about that delayed removal from the priority queue.
Right. Oh, absolutely. Removing a building too early can lead to, inaccurate skyline points.
Right.
It's all about the timing, making sure that building only leaves the queue when it's really, truly finished its contribution.
This is what I love about diving into these algorithms. There's always a level of nuance and careful consideration involved. It's not just about memorizing steps, it's about understanding why things work the way they do.
And what's even more exciting is that this isn't the only way to solve this problem. There are even more elegant and potentially even more efficient approaches out there.
Okay, now you've got me hooked. I can't wait to hear what other algorithmic magic we can uncover. Let's...
So are you ready to, step away from sweep lines for a bit
Yeah, for sure.
and explore, a completely different strategy?
Absolutely. Hit me with it.
Yeah.
What other tricks do we have for tackling these skylines?
Okay, so let's talk about divide and conquer.
Okay.
This approach is all about breaking a problem down into smaller, more manageable subproblems. You solve each of those independently and then merge the solutions to get your final answer.
I'm intrigued, but how do we divide and conquer a city skyline? It's not like we can just cut the city in half and calculate the skyline separately.
Right.
The buildings on one side would still affect the other.
You're right. We can't just arbitrarily split the city itself, but we can recursively divide the list of buildings. Think of it like splitting a deck of cards in half, then in half again, and so on.
Okay, so we keep dividing the list until we get down to individual buildings.
Okay.
I see where you're going with this. A single building skyline is easy. It's just a rectangle.
Exactly. That's our base case. Now, the clever part comes in merging the skylines of two subproblems to create the skyline of their combination.
That's where my brain starts to get a little fuzzy. How do we merge two skylines without ending up with just a chaotic, jumbled mess?
Okay, well, imagine you have two skylines, right? One from the left half of the buildings and one from the right half. And we're going to use a modified version of the sweep line technique to merge them.
Wait, sweep line again? I thought we were trying something totally different.
We are. But the core idea of that sweep line is still helpful here. Just instead of sweeping across all the buildings, we're sweeping across these two skylines.
Okay, so I've got two sets of skyline points representing those height changes, and our sweep lines moving across both of them at the same time.
Exactly. At each x-coordinate, we're going to look at the heights from both skylines and pick the taller one. And that becomes the height of our merged skyline at that point.
That makes sense, but wouldn't we end up with a ton of unnecessary points in our merged skyline if we're basically looking at all the points from both of the original skylines?
Yeah, that's where the modified part comes in. We only add a point to the merged skyline if the height actually changes from the previous point. So that way, we're making sure that we're only capturing the essential peaks and valleys of the combined skyline. No extra baggage.
Ah, that's clever.
Mm.
So we recursively break down the building list, find the skylines of those smaller pieces, and then use this modified sweep line merge to combine them back up.
Right.
It's like a bottom-up approach to building the skyline.
Exactly. And the efficiency is pretty impressive. So this divide and conquer strategy, combined with that merging technique, gives us a time complexity of, you guessed it, O of n log n, just like that priority queue sweep line method we talked about earlier.
But with all this recursion, isn't there some overhead involved, like in terms of memory, function calls? Could that slow things down in practice?
You're right, recursion does come with some overhead. In reality, the performance difference between the divide and conquer approach and the priority queue method might not be that huge. And it really depends on the programming language you're using and your specific implementation.
So it's a trade-off then. Divide and conquer is very elegant, very conceptually appealing, but that priority queue method might just be more practical in certain situations. It's cool how we're seeing all these different approaches and each one has its own strengths and weaknesses.
Absolutely. And there's one more approach that's worth mentioning, which uses a data structure called a union find to optimize the process even further.
Union find. Okay, that's a new one for me. Let's dive into that. But first, a quick recap for our listeners. We started our Skyline adventure with a brute force approach. Then we explored sweep lines. We uncovered the elegance of divide and conquer.
Yeah, and the key takeaway here is that there's no one best solution. Each algorithm has its own trade-offs in terms of efficiency, complexity, and, which scenarios it's best suited for.
Exactly. It's all about understanding the problem, considering the tools we have in our algorithmic toolbox, and choosing the best one for the job. Speaking of tools, I'm ready to add Union Find to my arsenal. What is this mysterious data structure, and how does it help us conquer these skylines?
So a union find data structure, it's all about managing groups of elements,
Okay.
and it really focuses on two main operations. You have union, which basically merges different groups together,
Right.
and then find, which tells you which group an element belongs to.
Okay, I'm picturing groups of elements, but I'm not quite seeing how that applies to buildings and skylines. How do those concepts connect?
All right, so think about it this way. Imagine we divide our x-axis into segments,
Okay.
each one representing a small slice of the cityscape.
All right, so we're breaking the x-axis up into these little chunks. I'm visualizing it like a ruler with markings for each segment. What's so special about these segments?
So each segment can either be covered by a building or uncovered, right?
Okay.
And here's where that union find comes in. It basically helps us keep track of which segments are covered by taller buildings so we can efficiently just skip over them when we're processing those shorter buildings.
Wait, so if a taller building covers a segment, any shorter building that overlaps that segment doesn't even matter for the skyline.
Exactly. The taller building already determined the skyline height in those segments. So that union find, it lets us group all those covered segments together so we can just bypass them.
Okay, I think I'm starting to get it. So we're basically optimizing the whole process by ignoring sections of the skyline that are already defined. But where do the union and find operations come into play?
All right, let's say we have a really tall building and it covers segments 2, 3, and 4. So using that union operation, we would group those segments together to show that, hey, they're all covered by this same building.
Gotcha. So then let's say we come across a shorter building, covers segments 3 and 4. What happens then?
That's when we use that find operation. So we would use find to quickly check if segments 3 and 4 already belong to a group that's covered by a taller building.
Right.
And in this case, they do. So we don't need to update the skyline for those segments. We can skip it.
Ah, I see. We're basically avoiding all those unnecessary calculations by using that information that's stored in the union find structure. It's like a shortcut that tells us which segments we can just ignore.
Exactly. And by processing the buildings in descending order of height, tallest to shortest, we make sure that we never have to undo any skyline updates.
Good.
We're always handling the tallest buildings first.
This is really cool. It's amazing how a data structure that seems totally unrelated can be used to optimize this problem so effectively. What's the time complexity like for this union find approach?
So it's still O of n log n because we're still sorting the buildings and their x-coordinates.
Right.
But the union find operations themselves are super efficient, making this approach really competitive.
Wow, this has been such an amazing journey through all these different Skyline algorithms. We've explored everything from brute force to sweep lines, divide and conquer, and now this elegant union-find solution. It's just fascinating how different approaches can tackle the same problem, each with their own levels of complexity and efficiency.
It really shows the power of creative problem solving, in computer science. And what's great is that these techniques can be applied to so many problems, not just skylines.
Absolutely. To all our listeners out there, I encourage you to take these ideas and see how you can adapt them to different challenges. Maybe use a sweep line to analyze stock market trends or apply divide and conquer to a really complex sorting problem. The possibilities are endless.
That's what makes coding so exciting. It's all about constantly learning, exploring, and pushing the boundaries of what's possible.
Well said. And on that note, it's time for us to sign off. Until next time, keep coding, keep experimenting, and keep those challenging problems coming.
And if you ever get stuck on a particularly tough one, you know where to find us. We're always up for a deep dive. Thanks for listening to AI.Code.Cast.